howdy there folks, hope you guys are having a good day. It is a lovely sunny day here today in Canberra, and we've got something very cool on the bench. Let me just bring it over for you guys to see. Whoa. Look at that. For scale, these are my hands. Apparently, this power supply weighs 8 kilograms. And it's a switched mode power supply, so that's a lot of weight. Ugh. If I switch it over, you'll see it is a Cisco Milan Plus AC/DC power supply, and it is rated at 42 volts, 55 amps, 2,500 watts maximum output power. This thing is ginormous, and it's going to make a great EV charger because for some reason, the output is also exactly the charging voltage for a 36 volt lithium ion battery, which is 42 volts. Now, obviously, we have to current limit this power supply or use some type of buck or boost converter in order to actually make sure we can regulate the charging current and things. But this is a perfect start for a high-speed EV charger, maybe at home, or something if I can change the style of enclosure, maybe something I could attach to a motorcycle. Anyway, I digress. Let's have a look inside. Whoops, before I get too far ahead of myself, here's the front side. We've got a 15 amp or 16 amp input connector, so not your standard kettle cord. We've got a switch here, which you have to have in the run position for it to power on. And we've got a big cooling fan. This runs all the time and it's pretty loud. And on the other side, we have our outlet air vent as well as our output current. We're going to change this, and fortunately this power supply, according to other internet sources, you don't actually need to do anything to make this run an output voltage, which is a lot different to some other power supplies I have in my shed where you need to hook up certain connectors in order to trick it into turning on. You don't have to do any of that for this apparently, so that's really good for us because it makes everything easier. Anyway, let's get into it. Wow, this is a hefty piece of equipment, and let's start with the top side. So as you saw, it's kind of a clamshell construction. There's two circuit boards on the inside, and this one is directly connected to AC mains. So at the back here, we can see a Qualcomm AC Filter. There's actually a circuit diagram on that filter, so I might just bring that up to show you. Yeah, so this performs filtering of some type on the AC line, and what that does is most likely it actually prevents voltage fluctuations and things from going back from the power supply into the AC mains. Otherwise, it just protects the power supply from any issues with the mains because of starting loads like fridges and stuff. Otherwise, you've got a massive 25 amp fuse here, much larger than a standard one. We've got our bridge rectifier with a heatsink on it. You can see it's one of those rectangular or square style bridge rectifiers. Very chunky. We've got a relay here. I reckon it's probably made for soft starting. So there'll be some sort of inrush limiting because you see how big these capacitors here are. If you connected those directly to 400 volts DC, they would suck up a huge amount of power in very short time and damage something, potentially themselves. So we've got that relay there. These big chokes, I suspect that's what they are. Otherwise, they're used in a DC to DC converter sort of circuit for power factor correction. Now, I don't have the knowledge or the expertise to go through power factor correction, but all I can say is that by using the DC to DC converter, this is able to more efficiently draw power from the AC mains. And that's about all I can say without getting super technical. And it reduces the amount of impact that this has on other devices connected to the grid. As you can see here, as marked on the board, we've got some transistors, because transistors are always marked as Q. So these are transistors, and yeah, so since these are transistors, this is probably going to be a DC to DC converter of some type. And this just looks after the power filtering. This is all high voltage. This is none of the step down. This is just to make sure this draws power correctly. And while I'm at it, let's have a look at this fan here. It's a 12 volt, 600 milliamp fan. Not the biggest one. I've got some really powerful fans somewhere. Oh yeah, check this out. Now this is a fan, 4.8 amps, very powerful, Delta Electronics brand. So not that sort of power, but this will still have grunt to get some airflow through. Switch mode power supplies, fortunately, are very efficient, so you don't actually have to cool them that much, but even so, they still make a little bit of heat, especially power supplies as large as this. Even 90% efficiency at 2,500 watts is still 250 watts of heat to expel. So moving on to the next section. Just go on and change the lighting, and hear me out, because I think that having direct lighting on the project makes everything look reddish, and I don't particularly like that, so forgive me for the change in lighting. I'm just doing my best to bring good videos to you guys. We've got our main switching mode power supply board here. The things that stand out to me when I look at it are the major heat sinks. These are high transfer heat sinks. So they're not very thick, but they're made to exhaust a lot of heat into the air because of the surface area. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 heat sinks. Actually, there's 2 of those. So 10 heat sinks in total. It looks like they're numbered, so it looks like there's 12 in total maybe. I digress. So we see the heat sinks. We've got our main transformers here. Now these are chunky. These are probably very similar to the size of the one I pulled out of a inverter welder one day. So they're obviously very powerful. If it's a 2500 watt power supply, each one will be doing 1250 watts. And that makes sense. Switching mode transformers are made for high frequency and have very low losses, and they're very efficient. So a transformer of this package could do 1200 watts, and that's just that's the beauty of the switching mode power supplies. Now we've got these thick wires, the black ones and the red ones. They're the 42 volt wires, so they're the ones we're going to be wanting to actually look at really. We'll focus on. We've got all of these extra ones. I'm hoping we won't even have to use this connector. We can remove this board completely and just use the red and black, because you've also got your high current 12 volt outlets, and I think it's only 10 amps at 12 volts, so it's nothing too serious. And I probably won't even use that apart from maybe a auxiliary supply to charge the 12 volt battery in my electric moped conversion. And also, that's another video I'm gonna do, so stick around for that one. Like and subscribe and comment if you want to see the electric moped conversion, because I'm having a blast with it. A literal blast, because I'm getting it sandblasted. I'm sorry. We got some small electrolytic capacitors. Now, usually I'd expect to see much larger ones. For a supply of this size and with this amount of current, you'd want a lot of filtering on the output. But I suspect what's going on is this supply connects to the computer, and the computer probably has a separate power filtering stage in it, which has all the big capacitors and everything. So this supply doesn't have to worry too much about being perfectly smooth or having really precise voltages. So hence the lack of energy storage. They do have a big inductor here though, so it's a 3 wires in parallel inductor. I'm not sure how many turns. Looks like 1, 2, 3, 4, 5, 6, bump the camera, 7, 8, 9 turn maybe. And that just goes directly from the main rectification stage to output diodes. This is an interesting design actually, because you'll see they have the main diodes here, and there's a whole big string of them. So you can see all of the traces on the circuit board. These parts are all diodes, and there's lots of them, but then it goes through the inductor to another set with only 2 diodes. And that confuses me, or at least it did, until I realized that what's going on here is these diodes here on the big heat sinks, they have to actually rectify voltage. So the input they're getting is high frequency alternating current from this transformer, or rather both of the transformers. And so they have a lot of, heating and stuff to do with actually having to convert AC to DC. Whereas these output diodes, they've only got a DC input direct from these first stage of rectification. So they're probably going to have less losses because they're just dealing with smooth DC current. Additionally, they're probably different package, or rather design of diodes. I imagine these would be Schottky diodes, and maybe these are also Schottky diodes. That just means they have a low voltage drop and they waste less heat. But maybe these ones are designed to work with high frequency and these ones are designed to work with high current, something like that. We've got our main switching transistors here. I'm not going to be able to show you really. I always post high quality photos in my description, so check those out if you want to see the part numbers and things. But just trust me on this. There's 2 transistors here, 2 transistors here, and they're in the classic TO247 format, which is just that larger style of transistor for the higher power supplies and stuff. We have some indicator lights here. They are input OK, fan OK, output fail. So not too much detail there, but you want the 2 green lights to come on when the power supply is all good, and if the red one comes on, you got something wrong. I'm trying to look around to see if there's any more circuitry that's actually interesting to you guys, because it's actually, nothing's really microprocessor based as far as I can see. It's all integrated circuits, which are just op amps. We've got a specific board here with some different things on it. Is this? Yeah, op amps, I think, as well, or comparators or whatever, comparators. And here we've got an SG3525 SMPS integrated circuit. And so I'm wondering if this entire power supply just runs off of these integrated circuits here. It would be handy if it ran off of these SG3525s, because these are really simple to set up for adjustable voltage, adjustable current and things, because that is all they're made to do. They're not a microcontroller that handles failures of the output. They don't communicate with the computer. They don't look at the input voltage from the AC output or whatever. They're just focused on switching these transistors on and off to get a power output on these leads. And that's really good for us, because much easier to look at what their circuit schematic is, and it's much easier to make changes if we need to make better use of this power supply. We have the capacitors. Sorry, I've got to check their voltage. They're 63 volt rated capacitors, so there is a bit of wiggle room on that side of things if I want to tune up the voltage to say 50 volts. But actually 42 volts is, as I said, perfect for an e-bike, so like a 36 volt e-bike battery, so I'm not too worried about that. Looks like we've got a current transformer here, so this is probably how they're measuring the power output. They do it on the AC side, and that's good because you don't need as thicker wires. Obviously, when you have high voltage, you have less amps for the same number of watts, because watts is proportional to both volts and amps. So cool, that's how they're doing it, and we can probably figure out where this goes to adjust the current limits and stuff on this power supply. and potentially even just set this up as an adjustable current and voltage power supply just as it is without having to add any electronics. Maybe add a potentiometer somewhere, but that could just be it, which is super cool in my opinion. Okay, I've rambled on long enough. I might make a part 2 of this video so you guys aren't sitting there forever, and in the part 2 we'll actually go in and see about starting the power supply up and then having a look to see what adjustments we can make to actually get this to do exactly what we want it to do, which is charge batteries at an adjustable rate. Guys, bless you. I hope you have a lovely day. Yeah, take it easy. You know, all of that good stuff. Bye-bye.